Hey, welcome back, my little flatbread crisps. We are going to talk about symmetry in functions and in graphs today. There are three different types of symmetry, or rather two types and one, I guess, non-type. You know what I mean? It's not a type of symmetry, it's just not symmetry. You feel me? So we're going to talk about what it means to be even, what it means to be odd, and then if it's neither of those two. So sometimes I feel like people say neither in a way that makes it sound like neither is a type of symmetry. It's not. You're saying it's neither even nor odd. So when it says identify the type of symmetry, I don't know. Sometimes English is tough. So we're going to talk about symmetry today. So let's dive in, shall we? Let's look at vocab first. So you're going to say, Mr. Barton, I've heard the word symmetrical before, but what does it mean when we talk about in math? So symmetry is when one shape becomes exactly being a key word here. Like another shape, when you flip it, slide it, turn it, in general, just transform it. So anytime we do a transformation and you get the exact same thing back, we say that there's some symmetry there. So we're going to start off by looking at even symmetry for graphs. And what that means is that it's symmetric over the y-axis. So to give you a visual idea of what this means, what color do you want to look at? Red? If we take a graph and we fold it on the y-axis, this point, when I fold it, will land exactly on that point. And this point will land exactly on that point and all the way across, right? This whole side will land perfectly on top of that side if we fold it in half on the y-axis. That's what it means to have even symmetry. Here's a little more strict definition, but we're not really going to worry about that, right? We're just going to worry about this easy definition. If I flip it on the y-axis, it looks exactly the same. Okay. Same thing here. If I took this and folded it exactly in half here, this stuff would land there, that would land there. This little peak would land on that little peak, and so on. So this would be an example of an even graph. Basically, if it looks mirrored on this side and this side, they look like reflections of each other, then it's even symmetry. Okay. There is also a type of symmetry called odd symmetry. Odd symmetry is a type of rotational symmetry. So what it means is odd graphs are functions where symmetry, hold on, let me try and read that again, are functions with origin symmetry, meaning it can be rotated 180 degrees. That's a half turn, right? It's like that far around the origin and look exactly the same. So let me show you what I mean on these two graphs. What I'm going to do is I'm going to trace this graph, and then I'm going to take the original and I'm going to rotate it half a turn around. Wow, isn't it crazy how it looks exactly the same? It lands on top of itself, kind of minus my poor drawing skills. But if you take it and you rotate it and you pin down the origin, meaning you let the origins overlap, then it should look exactly the same right side up as it does upside down. Let's check this one. This is a pretty interesting graph. So it curves down, comes back up. Right, so we're going to get a little goof right there, but c'est la vie. That's life. Right, kids? Let's make sure our origins line back up. Yep, and then we even have our little goof. So it's all right. But if we flip this 180 degrees and then make sure our origins line up, we're good to go. So that's what it means to have odd symmetry. There's maybe one extra thing you want to write down here. If it's going to have odd symmetry, the graph must, hang on, that's a W. Okay, your graph must go through, don't tell your English teachers, 0, 0. If it doesn't touch the origin, it cannot have even symmetry. All right. So the last type is neither. So if it's not like this, it's not even, and it's not like this, it's not odd, then you would just say it's neither, meaning it isn't either one of them. Okay. So let's look at a couple of graphs and determine if they are even, odd, or not either of them. Let me skinny my pen up again. Send that pen on a diet. All right. So if we look at this graph here, if we flip it or mirror it on this y-axis, this is going to land exactly on top of this. So this one is pretty obviously even. All right. If we look at this one, if I fold it here, that's not going to match up. It does look symmetrical, right? But if I fold it, this piece here is going to look like that. That's not landing on top of the rest of the graph, is it? Neither is that. But you can see that this isn't landing anywhere. So, all right, it's not even. Let's check odd. So it does go through the origin, but let's flip it upside down. Maybe let's trace it a little more carefully than I did the first time. I said more carefully. All right, close enough. If I flip this thing upside down, wow, that doesn't match up at all, right? This should be underneath this. It should look exactly the same. So it's not odd either. So this one would be neither. All right, one more example. Here's a nice graph that I made. All right, if I fold it on the y-axis, this side here is going to look like this. Oops, that's a little sloppy. Let's try that one more time. It's going to look like that. So we can tell that's not even. So even, nope. What about odd? Is it odd? So if we pin down our origin, and then let's trace it very carefully. Then we rotate it 180 degrees. Make sure your origins line up. Ooh, dang, that's pretty close, girl. So this one definitely looks odd. So this is an odd graph. Okay. And it's that easy. It's really not rocket science. All right. Now let's talk about end behavior, how we can figure out end behavior without a graph. And then the last thing we'll talk about after a couple examples is even and odd symmetry for equations, specifically polynomials. All right, so it says that our end behavior is based on the degree of the function, which is the highest exponent. So if I have like 3x to the third minus 4x squared plus 7, the degree here is 3 because our biggest exponent is a 3. So when we say degree, we're talking about the largest exponent on any of the x's. If something is going to have an even degree, the function's end behaviors are going to be the same. So if this number here is an even number, so 0, 2, 4, 6, or 8, or anything ending in these, then as x goes to negative infinity, f of x. As x goes to infinity, f of x. So if it's even, these two boxes, they must match. Okay, these two will be the same. Okay. Why did they do it this way? This is silly, you guys. All right. So if it has a negative even degree, then both ends are going to go to negative infinity. When they say a negative even degree, what they mean is the leading coefficient is negative. Okay. So first we're going to look at the exponent. If it's even, they're going to match. Then we will look at the leading coefficient and ask, is it positive or negative? Whoops, that's not a negative sign. Negative. that will tell us what direction our end behaviors go to. Okay. All right, we don't need to read the rest of this. This is silly. So let's look at our end behaviors here. So as x goes to infinity, f of x is going to do something. As x goes to negative infinity, f of x is going to do something else. Okay. So let's go ahead and copy this so that I can use it for later. Copy. Okay. All right. So the first thing we're going to do is we are going to check out our degree. So let's make sure it's in standard form. It is. This number right here is our degree. It is an even number. So what that tells me is that this box and this box, these have to be the same because this is an even number. It doesn't tell me what goes in them. It just tells me that they're going to match. Okay. Now we look at the leading coefficient and we ask, is it positive or is it negative? That will tell us the right side where x goes to positive infinity. So this one is negative, right? That's a -9. That tells us that the end behavior will go to negative infinity. Okay. Now, because this exponent is even, and I know they're the same, the left side must also go to negative infinity. All right, let's look at one more. All right, so we have our two boxes. This stuff is not important. Don't look at it. First, we look at our exponent. 6 is even. That means these are the same. We don't know what's in them yet. Now we look at our leading coefficient. It'll tell us the right hand of the graph, the positive side of the x. Because the leading coefficient is a positive number, that tells us we're going to go to positive infinity. They're the same, so this one is also positive infinity. All right. Let's maybe look at a couple of others. Let's make a couple up. So let's look at f of x equals -7 x to the 5th minus 3x squared plus 12. Okay. All right, so now we've got our two boxes. We're going to look at our largest exponent, which is 5. This is not even. This is an odd number. Okay, odd tells us, okay, if even means the same, guess what odd means? Just take a wild stab in the dark. Oh, you're right. That's so good. You guys are so smart. Oh my gosh, you're so good at inferring information. It means they're going to be different. So, if they're going to be different, let's figure out what they are. Okay, we know they're going to be different because of our exponent being odd. Now we look at our leading coefficient. It tells us the positive side of the x. So because our leading coefficient is negative, it tells us as x goes to positive infinity, on the right side, we're going to go down and go to negative infinity. All right. This one's negative infinity. They have to be different. So this one is going to be positive infinity. And there you go. Okay, that's just an example of odd. I just want to make sure it's in there so that you guys don't get super confused if you don't see it. All right, let's talk about determining if a function is even, odd, or neither. And we're talking about the symmetry again. We're talking about graphs that look like this, or maybe like this. This would be even. This would be odd. And then neither is just like random graphs. Stupid, ugly ones like that. Okay. So we can tell if a graph will be even, odd, or neither just by looking at its equation. For it to be even, all degrees, meaning every single exponent, has to be an even number. Let's talk about the weird thing here. constants, meaning numbers by themselves, numbers without x's, are considered even. So if you see f of x equals x squared plus 5, ignore the fact that the number 5 is an odd number. All we care is that there isn't an x here. This is like x to the 0, and 0 is even. So the number 5 counts as even though it's an odd number. So constants without variables are even. If all the exponents are odd, then it's an odd function. The weird thing here, I suppose, is if we have f of x equals x to the third plus x, there is an invisible exponent on x. It's a 1, and 1 is an odd number. So x's without exponents count as odd. And then if you have a mix of them, then it's neither. Okay. This is not a special case as long as you follow these rules. All right. So let's look at some of them examples. So f of x equals 8x squared plus 2x. Let's remember what the invisible exponent is here. It's a 1. So this number is even. This number is odd. That's a mix. So this function has no symmetry. Neither even nor odd. No symmetry. Okay. If we look at g of x, our exponent here is 3. That's odd. Our exponent here is 1. That's odd. Odd, odd. This is an odd function because every single exponent is an odd number. Okay, let's look at this one. Y equals 1/4 x squared minus 2. Don't freak out. I can feel you panicking already because you see a fraction. That's not even important for this question. All we care about are the exponents. 2 is an even number. Now let's remember our rule. Numbers by themselves are like x to the power of 0. 0 is an even number. So even, this is an even function. All right, h of x. We have an 8, we have a 3. We can stop there because this is even, this is odd. We have a mixture. This is neither. It's not even, it's not odd. It has no symmetry. And there you go. There are your notes. That's what you got to know. So hopefully that one's not too bad. That's a little bit short. I kept it under 20 minutes this time. If you have questions, please ask me. Please make sure you do your homework. And please don't do drugs, kids. All right. I'll see you guys next time.